This is Babitha, working as Assistant Professor in the Department of ECE in Institute of Aeronautical Engineering. In this session, I am going to discuss problems related to the power amplifier circuits. So, in this problems, we are going to calculate the input power from the power amplifier circuit and what is the output power we are getting from the power amplifier, and from that we can able to calculate the efficiency of the power amplifier and also the output voltage and how much amount of harmonic distortion we can get from along with the output of the power amplifier. So these are the parameters we are going to calculate in the case of power amplifiers. So these are different types of power amplifiers are available here. So the first power amplifier is Class A power amplifier. Actually, even though we are having the single stage and multi-stage amplifiers, and why we are going for the power amplifiers means in order to improve the power level of the signals, or else indirectly we can say voltage and current levels of the signal to high extent we are utilizing this power transistors or power amplifiers, so that we can able to utilize these power amplifiers in order to run the required practical applications with high frequency range of signals. So in the case of Class A power amplifier, so it can able to utilize total applied input signal for the amplification. That is nothing but one time one full cycle of the signal, that is 360 degrees signal, it can able to utilize for the amplification. So that particular power amplifier we are calling it as the Class A power amplifier. And while coming to the Class B power amplifier, so this Class B power amplifier can able to utilize only half of the input signal. It is utilized for the amplification. It is 180 degrees only. 180 degrees up to 180 degrees signal only it can able to utilize for the amplification. And while coming to the Class AB power amplifier, so this Class AB power amplifier is the compromise between the Class A as well as Class B power amplifier. So in this case, the conduction angle is less than Class A amplifier, but it is greater than Class B amplifier. So in this case, the conduction angle is between 180 to 360 degrees, or else greater than 180 or less than 360 degrees here. You can utilize that particular amount of signal here. So almost this particular amount of signal it can able to utilize for the amplification. And next one is Class C power amplifier. So the conduction angle of Class C power amplifier is less than 180 degrees. It is not even going to utilize the half of the applied input signal also. So depends upon the conduction angle we are making these four types of power amplifiers here. So Class D power amplifier is different for among all these four amplifiers. This Class D power amplifier used to design the digital circuits here, not for the analog purpose. So now we'll see the problems related to these different types of power amplifiers here. So we're coming to the first problem. First problem, it is Class B power amplifier. It is a classification of Class B power amplifier driven from a 24 volts power supply and driving a load of 8 ohms. From this, we need to find the DC input power as well as output power from the power amplifier, and as well as its efficiency if the peak-to-peak output voltage across the load resistance is 22 volts maximum value. So here the given values, the supply voltage is given VCC 24 volts and load resistance value is given it as 8 ohms, and the peak-to-peak voltage, the maximum peak-to-peak voltage is given as 22 volts. So from this we need to calculate input power, PAC input. So it is PVC input power we need to calculate, as well as PAC output power we need to calculate, and also the efficiency of this particular power amplifier circuit we need to calculate. So for that purpose, first of all, to calculate the powers, we require either voltage levels as well as current levels of the circuit here. Already they given peak to peak value. So from this we can find the DC current which is flowing in the power amplifier. So first of all, I am calculating the maximum voltage. Vm is Vm peak to peak divided by 2 here. It is peak to peak voltage 22 volts is given. So it is 11 volts in the positive direction and 11 volts in the negative direction, plus or minus 11 volts is the maximum applied input signal for the power amplifier. And from this Im, I can calculate the maximum peak of the current Im, that is equal to Vm by load resistance R. So Vm value here it is 11 volts and the RL value given it as 8 ohms. Okay. So if we simplify it one, we will get it as 1.375 amperes. This is the maximum current. So from this maximum current, we can calculate the DC current which is flowing in the amplifier circuit. That is 2 into Im by 1. So these are the formulas. So here 2 into Im value is 1.375 divided by pi. So if we simplify it, we will get it as 0.8753 amperes is the DC current which is flowing in the circuit. So from this DC current, we can calculate the input-output powers of the power amplifier. So the first one is input DC power we need to calculate. That is PDC is equal to VCC into DC current. Supply voltage into current. Voltage into current is the power. So supply voltage into IDC I am taking here. So the supply voltage is given as 24 volts and the IDC just now we have calculated, it is 0.8753 amperes. So it is 21.008 watts. The DC power from the amplifier is this much. And next we need to calculate the output AC power. The second parameter is output AC power, PAC. The maximum value of AC power, that is 1 by 2 into Vm square by RL. This is a formula to find the PAC value. So here we need to substitute 1 by 2. Vm value is 11 here, 11 square, and the load resistance value is 8 ohms. So this value we will get it as 7.56 watts. This is the AC power we are getting here. And the third parameter we need to calculate here, it is efficiency, that is PAC maximum, that is output power by PDC input power. So the AC power we got here it as 7.56 and the DC power is 21.008 into 100 by, because of percentage efficiency we are indicating in the percentage. So we will get it as 36%. So the DC power is 21 watts and the AC power is 7 watts and the efficiency is 36% we are getting from the given class B power amplifier. And next one is a single transistor is acting as ideal class B power amplifier again with a load of 1 kilo ohm. If the DC collector current is 15 milliamps and the supply voltage VCC is 20 volts. So from this we need to determine the efficiency of given class B power amplifier. So here the given values I am writing first. The load resistance is given as 1 kilo ohm and the IDC current, collector current IDC is given it as 15 milliamps and the supply voltage is 20 volts. This supply voltage is nothing but the maximum voltage whatever we are applying for the amplifier. And from this we need to calculate the efficiency value. So to calculate the efficiency, we require AC power as well as DC power, output AC power as well as input DC power. So for that purpose, first of all, I am calculating input AC power. PAC is equal to, here it is PDC, input DC power it has PDC, that is VCC into IDC value. So this VCC value given it as 20 volts and the IDC value is 15 milliamps. So it is 300 milliwatts of power we are getting here. And then next we need to calculate output AC power. Output AC power PAC is equal to again 1 by 2 into Vm square by Rn. And here 1 by 2 Vm is 20 volts divided by Rn. It is volts square. So if we simplify it, we will get it as 0.1 watts. The AC power is 0.1 watts we are getting here. And from this, we need to calculate the efficiency of the power amplifier. That is PAC maximum by PDC. It is 0.1 by 300 milliwatts into 100. So if we simplify it, we will get it as 33.33% as the efficiency of the given class B power amplifier. And we'll coming to the next problem. A power amplifier supplies 3 watts to a load of 6K. The zero signal DC collector current in 55 milliamps and the collector current with signal is 60 milliamps. How much is the percentage in second harmonic distortion here? It is nothing but from the given power amplifier how much second order distortion we are getting, we need to calculate here. So for that purpose, first of all, I'm writing the given parameters. The power is given as 3 watts and the load resistance value is 6 kilo ohms. And here the given two values collector currents IC equal to 55 milliamps. This is whenever zero signal, when we are not providing the input signal to the amplifier. And the next current we are getting here it as 60 milliamps. This is with signal. Okay. So here we need to calculate the percentage of second harmonic distortion D2 here. We are representing with the D2, second harmonic distortion. So here to calculate the harmonic distortion, second harmonic distortion, we have to take the dynamic characteristics of the power amplifier. So by using dynamic characteristics, these are already discussed in the theory concept of power amplifiers. So from this we can write here it as IC equal to G1 base current IB plus G2 IB square here. This is from the dynamic characteristics we are writing here. So here we have the B2 value we need to calculate by using the collector current with signal minus the collector current with no signal. So here collector current with signal is 60 milliamps and this one is 55 milliamps. So is 5 milliamps the value of B2 is. And next we need to calculate the fundamental component of the power. Fundamental component of power P I'm taking, that is V1 square into load resistance RL by 2 here. So V1 value is So from this here we have power value as well as load resistance value. From this we can calculate the value of B1 here. So B1 square I can write it as 2 into P by R. So 2 into power value is 3 watts. This is RL only. So RL value is 6 kilo ohms. So this value we will get it as 0.0316 amperes. B1 fundamental component of the power. From that we can calculate the B1 value as 0.0316 amperes. And next we need to calculate the second harmonic distortion. The second harmonic distortion D2. The formula for this is B2 by B1 into 100%. So here B2 value is, we have already calculated 5 milliamps, and the B1 value is 0.0316 amperes into 100%. So that is 15.82% of second harmonic distortion is present in the given class B power amplifier. So along with the required signal, this amount of second harmonic distortion is also appearing across the class B power amplifier. And now, while coming to the next problem, it is a single stage class A amplifier. Till now, we discussed about the class B power amplifiers. So now it is class A power amplifier. So here, the given values, the supply voltage is 20 volts given, and the Q point values, the quiescent operating point values of the amplifier are given it as VCEQ is 10 volts and ICQ is 600 milliamps. So that we can write it as Q ICQ, VCEQ values are 600 milliamps, 10 volts here. So with this, with these values, it will operate in the proper active region to make it as the amplification. And AC output current is varied by plus or minus 300 milliamps. Okay, the maximum current which is flowing in the circuit is 300 milliamps with the AC input signal. So from this, we have to find the power supplied by the DC source to the amplifier circuit. That is nothing but PDC input power we need to calculate. That is the first bit. And next, DC power consumed by the load resistor. It is nothing but PDC output power. And next, AC power developed across the load resistance. That is PAC. And next, DC power delivered to the transistor. To the transistor, how much DC power is flowing. And DC power wasted in the transistor collector. And how much DC power is wasting across the transistor. And next, we need to calculate the overall efficiency of the circuit, and also across the collector, how much efficiency it is providing. So these are the parameters we need to calculate from the class A power amplifier here. So here the given values are the supply voltage 20 volts and the operating point values are this much, and the load resistance is 16 ohms and the maximum current is 300 milliamps. So here the first bit we need to calculate is power supplied by the DC source to the amplifier circuit. So that we can calculate from the supply voltage as well as the quiescent current. So that's why I written it as PDC equal to VCC into ICQ. So the VCC value is given as 20 and ICQ value is 0.6 here. So the value of DC power supplied to the circuit is 12 watts here. And next bit is DC power consumed by the load resistor is given it as, that is nothing but we have to calculate the PDC by utilizing the load resistance along with the quiescent collector current. So that's why I have taken here it as ICQ square into RL here. So that is 0.6 whole square into 16. 5.6 watts of power is consumed by the load resistor in the amplifier circuit. And next, AC power developed across the load resistor is PAC here. To calculate that PAC value, we require the maximum current I here. So to calculate that maximum current I am taking Im by root 2 here. So the Im value is 0.3 here divided by root 2. We will get it as 0.212 here. And the AC power, it is current into resistance, I square into load resistance. I value is 0.212 whole square into load resistance is 16 ohms. So we got it as 0.72 watts. And the next DC power delivered to the transistor. How much amount of DC power delivering to the transistor? We are indicating with P transistor DC. So how we can calculate that one means from the overall DC power, we have to remove the DC power across the load resistance. If you take the difference of the two, we can able to estimate how much amount of DC power delivered to the transistor. So that's why I am taking here it as PDC minus PLDC. That is 12 minus 5.76. The value it as 6.24 watts here. And next, DC power wasted in the transistor collector is that we can calculate if we take the difference of how much power delivered to the transistor as well as how much AC power delivered to the power amplifier. If we take the difference of the two, we can able to find how much amount of power is wasting across the transistor collector. So here P transistor DC we have calculated 6.24 watts and AC power is 0.72 and this value is 5.52 watts here. And next, to find the overall efficiency, that is AC output power by DC input power, PAC by PDC into 100. So that we will get it as 6%. And next, how much amount of efficiency we are getting across a transistor collector, that we are indicating with eta C here. That one we can calculate from the output AC power as well as how much amount of power delivered to the transistor, that is PAC by P transistor DC here. That is 0.72 by 6.24, that is 11.5% of collector efficiency we are getting here. So these are the desired parameters from the given problem. And next, coming to the next problem. It is class A power amplifier with a direct coupled load as a collector efficiency of 30%. So they given the efficiency value 30% and delivers a power input of 10 watts. So input power is 10 watts given it is. So from this we need to calculate DC power input, that is PDC input as well as power dissipation of full output, that is how much amount of power dissipation or power is wasting we have to calculate. And next, desirable power dissipation rating of the BJT. So these three values we need to calculate from the given class A power amplifier. So here the first one we need to calculate here it as efficiency, that is output power by input power. So here we don't know the value of DC power. So to calculate the DC power, I am writing here it as PDC equal to PAC by efficiency. Here we have the values of AC power as well as efficiency. If we substitute the two values, we will get the DC power as 33.33 watts here. And next, how much amount of dissipation across the output, that we can calculate from the total DC power PDC minus here 5 we are taking here it is PDC minus 5, that is 33.33 minus 5, it is the 28.33 watts of dissipation we are getting across the output of the transistor. And next, how much amount of dissipation we are getting whenever we are not getting the output across the amplifier. So that one we are indicating again with the DC power 33.33 watts. So that is the BJT rating of the dissipation. How much amount of power dissipated with no input indicates the power rating of the BJT transistor, that is 33.33 watts here. And next one is calculate the input power and efficiency of the amplifier shown below for an input voltage resulting in a base current of 10 milliamps peak. Also calculate the power dissipated by the transistor. So this is the class A amplifier given here, okay, with the collector resistance 20 ohms and the base resistance 1 kilo ohm, and the current amplification factor is 25. So from this amplifier we need to calculate the power efficiency first thing, and also we need to calculate the input power to the amplifier, and also how much amount of power dissipated across the transistor we need to calculate. So here to calculate the DC power, how much it is delivering into the transistor, we require the DC current first. So to calculate this DC current, we require the maximum current. To calculate this maximum current, we require the maximum voltage for the circuit. So that's why, first of all, we are calculating the Q point values of the transistor. So to calculate Q point value, first of all, we require the base current. So by using the base current and current amplification factor, we can calculate the overall collector current. So the base current from the amplifier, so the base current will be flowing here, IB. So that we can write it as this one VCC, supply voltage, minus this drop, base to emitter voltage, divided by this resistance RB here. So VCC minus VBE by R. So VCC value given it as 20 volts, and the base to emitter voltage of the silicon transistor is 0.7 volts here, and the base resistance is 1 kilo ohm given in the circuit itself. So if we substitute all that values, we are getting the base current as 19.3 milliamps. So from this base current, we can calculate the collector current, that is the multiplication of the current amplification factor into input current. So if we substitute the two values, we will get it as 482.5 milliamps of the collector current here. So this collector current is one of the point of the operating point. And next we need to calculate VCEQ, the next point of the operating point. So to calculate that VCEQ value, I am writing from the output side of the circuit. From the output side of the circuit, I am applying KVL. If I apply KVL across the output side, I will get it as VCC minus drop across RC, that is IC into RC. So VCC minus IC into RC. So the supply voltage is 20 and the IC value we got it as 482.5 milliamps and the collector resistance is 20 ohms. So if we simplify it, we will get it as 10.35. So the the Q point value here it is 482.5 milliamps and VCQ is 10.35 ohms. So at this corresponding voltage and current, this power amplifier can able to provide the maximum amplification without any distortion. And next we need to calculate the AC power. So to calculate that AC power, we require the AC current. So to calculate that AC current, I am taking AC peak value. That is equal to beta into IB peak value here. So IB peak value, how I can calculate here it as From the IB, it is 19.3 milliamps. I am approximating here it as 20 milliamps to make it as 10 milliamps in the positive direction and 10 milliamps, minus 10 milliamps in the negative direction. So 10 milliamp peak to peak amplification here, peak to peak current here it is 10 to 10 milliamps. So that's why to find the peak collector current, I am taking one of the peak current of the base current. So beta into IBP, that is beta value is 25 and the positive peak base current is 10 milliamps. So we will get it as 250 milliamps. So the AC power is equal to a maximum peak collector current divided by root. That is 250 milliamps by root 2. If we calculate, we will get it as 0.625 watts. So this much amount of AC power coming from the power transistor. And next, DC power. How much amount of DC power we are getting from the circuit? That is VCC into IC here. So VCC is 20 and the IC value is 482.5 into 10 power minus 3. It is 9.6 watts here. And by using this AC power as well as DC power, we can calculate the efficiency PAC by PDC. If we substitute that values, we will get it as 6.48% of efficiency here. And next parameter we need to calculate here it is how much amount of power dissipated by the transistor across the collector. That is PC equal to DC power minus AC power. We substitute the two values, we will get it as 9.025 watts of power is wasting across the collector of the given power amplifier. So in this way, we need to calculate the parameters from the given parameters of the power amplifier. So in this session, we discussed the problems related to the class A as well as class B power amplifiers, and from that we have calculated the how much amount of output power as well as input power consuming from the power amplifier, and how much output voltage and the collector current we are getting from the transistors. And also we have calculated how much amount of efficiency we are getting from the transistor, and also the how much amount of power dissipation we are getting when we are operating the power amplifiers. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.